Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So good morning. Thanks for coming. It's my great pleasure to introduce Atish Das Sharma from the Georgia Institute of Technology. And his work spans quite a few different areas and also quite a few different conferences. So among others, he has papers at Wisdom, KDD, VLDB, PODC, ESA, and a Best Paper Award at PODS. He's going to talk about two of them. And if you sort of talk to him later, feel free to ask him about his other work. Thank you very much.
Thanks. So yeah, I'll be talking about efficient random walk computation and ranking mechanisms on the web. A quick outline of the talk. So in the first part of the talk, I'll describe our work on performing random walks efficiently, specifically on graph streams. And this will lead us to an efficient streaming algorithm for estimating PageRank. And I'll briefly mention similar results we have for distributed networks. And in the second and much shorter part of the talk, I'll describe work on understanding ranking mechanisms employed on the web. Specifically, we'll review and analyze user feedback-based ranking mechanisms. And finally, I'll quickly summarize all of my work. OK, so random walks are a fundamental tool used across many different areas in computer science. They form the basis of understanding Markov chains. They have several applications in web algorithms. In high-dimensional geometric objects, random walks are used in estimating volume and sampling. And random walks have been traditionally used for several clustering and partitioning applications, and also are useful in distributed computing theory. And random walks also play a key role in certain mathematics and statistical physics problems. So I'm specifically interested in algorithms and algorithms for large data sets and large graphs in particular. So the areas I'm interested in for random walks is the web, social networks, and distributed networks. And just in this domain itself, random walks play a key role in several different applications. For instance, random walks are useful in search, in ranking, in similarity detection, in general understanding the connectivity structure of graphs, and thereby also graph partitioning and finding graph cuts. And then in distributed networks, they have a whole range of other applications, such as load monitoring, malicious behavior detection, and so on. So what is a random walk? Random walk is an extremely simple operation by which you transition from one state to another state in a possibly infinite set of states. And this is an iterative process. So I'll try to define it for graphs, because we'll only be dealing with graphs in this talk. So let's try to understand it through an example. So you have this large graph, and the random walk starts at one given node. So here, let's say it starts at the orange node. And in the first step of the walk, you transition to one of your neighbors. So you transition to one of the nodes. So here, think of nodes as the states. So you transition to one of the neighboring nodes uniformly at random. So here, there are 4 neighbors. You transition to any one of them with probability 1/4. So let's say you take the purple edge here. So that then after one step of the walk, you end up at the new orange node. And then you repeat the random walk from this orange node. Again, this orange node has 4 neighbors, and you transition to one of them uniformly at random. And the important point is, it doesn't matter where you came from. The next step of the walk is entirely determined by where you are currently. So again, here you have 4 neighbors. You transition to one of them uniformly at random. Let's say you take the purple edge again, that's going to the right. That pushes you to this orange node. And now this is a random walk of 2 steps from the given source node. And you continue the process similarly. So again, you are at this node, sample one of your neighbors. And suppose you wanted a random walk of 3 steps. This is a 3-step random walk, and you have sampled a destination. So this is how you perform a random walk. And I presented it here for undirected graphs, but it can similarly be defined for directed graphs. So in a directed graph, you transition to one of your out neighbors. So at any given point, you are at a given node. You look at your out edges and sample one of them uniformly at random. So this is the random walk process. So why are random walks so powerful? It's this extremely simple operation, but it has so many different applications. And there are many different reasons for this, but I'll try to give you an algorithmic intuition as to why random walks are powerful. So let's try to understand this by a large graph where we think of edges between nodes as reflecting some kind of similarity between nodes. So two nodes are connected by an edge if there's some kind of similarity or correlation between them. For instance, on the web graph, a given web page points to another web page, possibly because there's some relation between them. Or in social networks, two nodes or two people on the network are connected if they've explicitly formed a friend edge between them. So they're friends. So think of edges or links as representing some kind of similarity. And now suppose we are trying to find similarity between nodes that are not explicitly connected by an edge. So in case of social networks, suppose you're trying to make friend suggestions or friend recommendations between two nodes that are not connected by an edge. So how do you go about doing this? Again, under the hypothesis that given edges reflect some kind of similarity. So the first try could be shortest paths. So let's say I'm trying to find nodes that are similar to S, node S here, but are not directly connected to S. I know that nodes that are connected to S are similar, but what about nodes that are at distance 2 from S? They have nodes that you have common neighbors. So, or there's a short path from S to nodes that are at distance 2. So a distance 2 path. So then you have a node that is similar to both the S and the node you're looking at. So this possibly is a good indication of some similarity between S and the node at distance 2. And so shortest paths could be a good way to go about it. But now let's look at S and C in this graph. So in this graph, S and C are extremely far away, but they have many common paths between them. So there are many long paths between S and C. What can I say about one long path? One long path between S and C is an extremely weak correlation between S and C, because there is a link, there's a path of similar edges. So one path is a weak correlation between S and C. But now if I have many paths, the correlation gets reinforced as the number of paths increases. So a good measure of similarity could be the number of paths between two nodes. And random walks beautifully capture both these intuitions. So there are various ways to define the random walk-based similarity between two nodes. But under any reasonable definition, the random walk-based similarity between two nodes is determined both by the number of paths as well as the distance, or the number of short paths. So it gives weights to paths based on distances. So random walks turn out to be fairly useful for discovering similarity between nodes. So let's look at another setting where I'm trying to do some kind of graph partitioning. So I have this massive graph, extremely large graph, so I have no idea of the topology. But there is some inherent topology in the graph. In this specific case, let's say there are three connected components, three expanding components. So by expanding, I mean they're in some way well connected within, but sparsely connected across. And now I'm trying to mine this community structure of the graph. I do not know this, but I want to try to understand the community structure. So again, in social networks, so you have the whole network of users, and probably I'm trying to find a set of users that form some kind of a well-knit community. So how do I go about doing this? Let's say, again, let's try to understand why random walks are useful here. Suppose I'm trying to find the community around the node S. So what could be one try? Again, I could try to find the nodes that are near S in terms of graph distance and say that that forms a community. But notice that even though C1 and C3 or C1 and C2 are very sparsely connected, they do have one edge or a few edges directly connecting C1 and C3. So there could very well be nodes in C3 that are extremely close to S in graph distance and could even be closer than nodes in C1 itself, and similarly C2. So if I try to just look at the nodes that are near S, it's not clear that I'll really understand this kind of strongly connected structure. But random walks turn out to be helpful here. For instance, suppose I start by doing one random walk or a few random walks from the node S and look at the nodes I visit. It turns out that you are very likely to visit most of the nodes in C1 before you visit too many nodes in C2 and C3. So this automatically suggests an algorithm to understand the community structure. So if I want to find the community around S, do several random walks from S, look at the nodes you visit, do walks of certain length, chop it off at some length, and you get a set of nodes you've visited, and that sort of gives you the community around S. And this actually can be made precise in terms of a fairly non-trivial theorem, but that's really the intuition. So random walks are used for this sort of graph partitioning application. Okay, a third reason why random walks are useful is because of the steady state distribution they induce. So what do I mean by this? So I can perform random walks of any given length. Suppose I perform a walk of extremely long walk, so long that it really doesn't matter where you started. Then this induces a probability of ending up at any given node. And it turns out that the probability of ending up at any given node after a long walk is a very good measure of the importance of that node in the overall graph structure. So for instance, in undirected graphs, it turns out to be proportional to the degree. So after a long walk, the probability of ending up at a node is proportional to its degree. And one can imagine that a high degree node is sort of well connected and probably important for that graph structure. Similarly, for directed graphs also, this steady state probability is a good measure of importance. It's sort of harder to compute. But it again reflects the importance of a given node. And suppose you want to sort of find the nodes that are important with respect to a given region of the graph or with respect to certain nodes. Then the random walk transition can be modified such that you capture this intuition. So for a given region, you can modify the random walk such that the steady state probability gives you nodes that are important with respect to this region. Okay, so these are some of the reasons why random walks are useful. And so we would like to leverage these properties of random walks and help with our application. So what is the difficulty? You're typically trying to do this on massive graphs, extremely large graphs, hundreds of millions of nodes or even possibly billions of nodes. And then most applications require many walks and long walks because you would like to cover a large part of the graph. And computational cost becomes an issue. And another difficulty is, the graph is so large that you really cannot store it in main memory. It's stored on disk, and you have some form of restricted access. So how do you reconcile this situation? And one difficulty in distributed networks, by which I mean something like a peer-to-peer network, is that nodes have only local knowledge. So in a peer-to-peer network, a given node wants to perform this global computation, say wants to sample from a long walk. But it can only interact with the nodes, the neighboring nodes. So you have local operations, but you want to perform this global computation. So how do you go about doing this? So in this talk, I'll mention how we overcome all of these challenges. So how have random walks been done traditionally? It is a naive solution that you sort of do it iteratively. So given a source node, suppose you want to perform a walk of length L, what do? You start from the source and sample one of your neighbors. You want a walk of length L, sample one of your neighbors uniformly at random, and ask for a random walk of length L minus 1. Because a walk of length 1 plus a walk of length L minus 1 is a concatenated walk of length L. And now once this node has been sampled, again you ask, that node in turn samples one of its neighbors and asks for a random walk of length L minus 2. And then now notice that before you reach this node, you have no idea where you'll be 2 steps later. But once this node has been sampled, again the node samples one of its neighbors and asks for a random walk of length L minus 3. So you're proceeding in this sequential manner, one step at a time. And again for length 4 and 5 and so on. Suppose you wanted a walk of length 5, you finish after these 5 sequential steps. So random walks have always been performed in this inherently sequential manner. And this has been used in most different settings and for most applications. So the question is, can we do better? That was the motivation of part of this work. And so in a series of papers, we've shown an extremely powerful technique to perform random walks in parallel. So a parallel algorithm for performing random walks. I'll specifically describe the streaming algorithm for performing random walks in this talk. And this is applicable for web graphs. And we've shown how this is useful for computing PageRank vectors as well as for cuts or for graph partitioning. And we have similar results for performing random walks in this distributed setting. And this also can be used, our algorithm can be used for estimating mixing time, which is a good measure of how connected a given graph is, and also for sampling from random spanning trees. So in one slide, let me try to mention what I'll present in the first part of the talk. So you're given this graph, you're given a source node, and you want to perform a random walk of length L. So how has this been done traditionally? You start from the source, proceed sequentially until you finish L steps, and then you reach a destination. And that gives you a random walk of L steps in L iterations. What we show is how to do this faster. So start from the source and somehow quickly jump ahead. And once you jump ahead, again jump ahead further. Instead of doing it sequentially, sort of jump ahead rapidly and then reach a sample destination. Specifically, we show how to do this in root L iterations. And what is important is you still get a true sample. You do not even get an approximate sample. You get a true sample from the distribution at length L in just root L iterations over the graph. So let me define the streaming model, because I'll present this work, this algorithm for graphs presented as streams. So the basic premise of the streaming model is you're dealing with large data set that definitely cannot be stored in memory. So it's stored on disk, and you have sequential access to the input. So in this case, we're dealing with graphs. So the graph edges are stored on disk, and as the algorithm proceeds, it maintains small memory, but has sequential access to the edges of the graph. So what does this mean? As an algorithm, you start by looking at the first edge, then you look at the second edge, then you look at the third edge, and so on. You're not allowed to retrace. You're looking at the edges of the graph sequentially, and you perform one entire pass over the entire input. And if necessary, you can perform, if you need to look at something again, you can start a second sequential pass over the input. In the middle of a pass, you're not allowed to retrace, but you can perform a second pass, start at the beginning, and again scan the entire input sequentially. So how much space is stored on disk is the number of edges in the graph, and typically how much memory are you allowed while performing the algorithm, performing passes. You're typically allowed space proportional to the number of nodes in the graph. So notice that this can be larger than the number of edges. And it turns out that for constant number of passes, you need linear space in the number of vertices, even for very simple properties such as testing graph connectivity or bipartiteness. So this, in some sense, is the best you can do in terms of memory. And so the goal is then to, and how are the edges presented? So there are different models, but the most general setting is that you have no control over what order in which you're reading the edges. It's some adversarial order. But this model has been studied extensively, and several variants to this have been considered, such as randomized order or some kind of special order. So under this setting, what are you trying to do? You're trying to minimize the number of passes, minimize the number of sequential scans over the entire input for whatever computation you want to do. So in our case, we're trying to do a random walk. You're given a source node U. You want to sample from a random walk of length L. So you reach some destination V. And let's say that you don't really care about the walk. You only care about the destination. Yeah?
The question, are you really doing a single random walk, or you do multiple in parallel?
Yeah, so later we show how to do many walks. So you want to do many walks. But the key technical insight comes from how you do one walk, and then I'll mention how we do many walks. So that's our goal. So recall we are under the streaming model where you have sequential access. So what is the naive techniques? Let's try to do a random walk. You have a source node S, and you want to do a random walk of length L. What can I do? In the first pass, I can try to wait for the edges incident on S to stream by, and I can sample one of them. Because the first step of the walk is one of the out edges corresponding to S, sampled uniformly at random. So perform one pass, wait for the edges incident on S to arrive, sample one of them uniformly at random, let's say A. But now suppose I want to make another step of the walk in the same pass. It's not clear how you do this, because the edges corresponding to A might already have streamed by. So what can you do once you are at A? You can again start from the beginning, perform another pass over the entire input, wait for the edges incident on A to arrive, and sample one of them uniformly at random, and this pushes you to B. Again, when you were at S, you did not know where you'll be 2 steps later, so it's not clear how you do a third step in just 2 passes. Once you are at B, again what you can clearly do is look at the input again, sample one of the edges neighbors of B, and in the pass, and that say you sample C, and then you finish the pass, and so on. So from C, again, you can sample one of its neighbors in one pass. So what is happening? You're performing one step of the walk with every pass over the entire input. And you can continue this pace from C, again sample one of its neighbors, and so on. So what does this give us? A walk of length L can be performed in L passes over the entire input. Constant space, because I'm only I'm not interested in the walk, I'm only interested in the sample, the end sample. So I can store the current position I'm in. And you need L passes. So now suppose you really want to cut down on passes, even at the cost of increasing the space beyond linear. So this is not technically allowed, but just to get intuition, what would you do then? Suppose I really want to do it in one pass. I could, if I was allowed to store more space, I could certainly store the entire graph in one pass, and then I have the whole input and do whatever I like. So can one do slightly better than that? I could try to sample a sufficient number of edges. So if I want to, let's say if I want to do a walk of length 2, if I sample 2 out edges from every node and then store this in memory, then I have, the sample edges gives me sufficient information to perform a walk of length 2. So this suggests an NL space algorithm for a walk of length L, sample L out edges from every node. So in NL space and a single pass, I can again perform a random walk of length L. So these are the two extremes. So you can do either L passes or one pass, but then space goes up to NL. So what do we show? We show how to perform a walk of length L in root L passes and in linear space, which is allowed. But compare this to the first naive technique. We've brought down the number of passes from L to root L. But space has gone up significantly, which can be, so what can we do about that? So in fact, it turns out that we can really do a large number of walks, specifically N over L independent random walks, without increasing the space at all. So in terms of space, the amortized space is not large, but the difficulty really lies in bringing down the number of passes, and we bring down the number of passes from L to root L. So I'll try to present this algorithm now. So the key insight is really to perform short walks from all nodes and cleverly merge them together. So we are trying to do a walk from one given source node. But what was the difficulty with the first naive technique? I had no idea where I'll be 2 steps later. I could be anywhere 3 steps later or 4 steps later. So with this hindsight, try to do short walks from all nodes in parallel, in the hope that if you reach them, you can reuse these pre-computed short walks. So let's try to do that. So perform short walks from all nodes. Specifically, perform walks of length W from every single node. One walk of length W from every single node. Think of W as about root L. So you're doing this in parallel. So how many passes do you need? By the simple algorithm, the first algorithm, you need W passes. Each of this is done naively. And how much space? I'm storing one walk from every node, one source destination pair. So that's N space. So I've used root L passes so far. And now what? I've computed this. Now start from the source node and try to merge these together. So specifically, you're at X, and now start merging the walk. So from X, I've already pre-computed this. Now I'm not looking at the stream again. I'm just looking at this, this pre-computed information that I've stored in memory. From X, there's this short walk, and I can jump to A directly. And now what happens at A? I've pre-computed a short walk from every node. Specifically, there's a short walk out of A also. And now this is stored in memory. So without looking at the stream, I can again from A jump ahead to B. So I'm getting a concatenated walk. And then from B, again there's a short walk of length W out of it. And from B, I can again stitch it together and jump to C without looking at the input. I'm only looking at what I've pre-computed. From C, again, there's a short walk, and you stitch that together, and you jump to D. And the hope is you keep stitching these, and hopefully you finish a walk of length L. But of course, there's a difficulty. What if you return to a node, say B, a second time? I had stored only one walk from every node, and from B, I have this short walk of length W. But I've already used it up. And I really cannot reuse it, because if I reuse it, I'm destroying the randomness of the total stitched walk. So how do you deal with this situation? So let's try to do that for another example. Suppose you started from the node X, and you did these short walks, merged them together, went to B, C, D, E, and back to C. So now you're stuck at C, and you want to extend the walk, and it's not clear how you extend it without looking at the input. From my information in memory, I do not know how to proceed. So what can I do? I can try to sample edges out of C. I'm stuck at C. I can try to sample S edges out of C. Specifically, sample S edges out of C. I could just sample one edge out of C, and that will push me out, and hopefully I can extend the walk. But if I end up at C or any of these nodes, X, A, B, C again, I'm going to be stuck. So what we do is now invest one pass and sample S independent edges from all of these nodes, X, A, B, C. I'm really stuck only at C. But why am I doing this? Because again, you're trying to think ahead. Because if you end up at X, A, or any of these nodes, you have already used up the short walks. So I'll get stuck. So to avoid getting stuck in the future, sample these S edges from all nodes. Again, think of S as about root L. And now what can I do? From C, take the first sample edge out of it. Let's say this puts me at F. Now I've escaped out of the stuck node. But now what can I say about F? F is either one of these nodes outside, whose short walk I have not used, or it is one of the nodes whose short walk I have used. There are only two possibilities. So if it's one of the nodes whose walk I've already used up, then if it's one of these, if F is one of these nodes, X, A, B, C, then what can I say? I was already careful in sampling a few extra edges. So I can still get out by using one of those edges. In particular, if I visit any of these nodes the ith time, I can use the ith edge out of it. I have S independent edges. So I can visit each of these stuck nodes at least S times before really getting stuck. And if it is not, if you don't go around these stuck nodes, if F is one of the nodes outside, that is great, because then I have short walks of length W out of them, and I can just extend the walk quickly further ahead. So in some sense, you're either making S progress or W progress, the latter being because you're visiting a new node. And that really finishes the algorithm, and that's the whole algorithm. So to quickly summarize, you start by performing short walks from all nodes, then start from the source and start stitching these together. And as you stitch them, you might get stuck at certain nodes, but if that happens, you sample these additional edges by investing an additional pass over the entire input. And then you try to make this local progress until you escape to a node outside. So what is happening? You're either making S progress, this is in an amortized sense, you're either making S progress or visiting a new node. And if you visit a new node, you make W progress. And so you're making S or W progress. And the analysis is also extremely simple. So this immediately gives a root L pass and N plus L space algorithm. Why is this? Think of S and W as about root L. And now you're making at least either S or W progress in every pass. And you're doing a walk of length L. So the passage is just root L. And how much space do I need? In the first pass, I stored N space where I did short walks from every node. Now the second phase of the algorithm, I'm sampling edges from certain number of stuck nodes. In particular, I'm sampling S edges from stuck nodes. So how much space can this cost me? How many stuck nodes do I have? In total, I'm performing a walk of length L. And every two stuck nodes are separated by a random walk distance of W. So the number of stuck nodes is at most L over W. And so the space is at most L, because W is S. So that gives the bounds. So in the paper, we further generalize it to show how for any parameter alpha less than 1, you can perform a walk of length L in root L over alpha passes and N alpha space. And the reason this is nice is because you can make the space sublinear. So yeah, now the goal is to perform many walks. So unfortunately, I won't be able to go into the details, but I'll just try to mention the intuition of how to do many walks. So naively, by naively I mean suppose you try to use our algorithm to perform k walks how in parallel. How can you do it? You can do it in kn alpha space if you don't want to increase the passes beyond root L. In parallel, I can run k executions of this algorithm, and that takes kn alpha space, and the passage doesn't go up, it's just root L passes. But what we show is how to do, without increasing the space at all, perform a large number of independent walks, n over L in particular. And the intuition for this is really to notice that in a walk of length L, you use only a few short walks. You stitch only a few short walks, but there are many nodes whose short walks go unused. And so the goal is to try to figure out which nodes I'm more likely to visit and store more short walks from those nodes and very few, if any, from the other nodes. And how does one try to learn which nodes to store more walks from? So this is sort of a doubling trick where you start by performing one walk and see which nodes you used up, and then do two walks and see which nodes you used up again. And slowly you get better and better estimates of which nodes you're more likely to visit. So you start by 1, 2, 4, and so on. And that's really how you can do k walks. So it's technical, but there's no real no big insight there. So yeah, so that finishes the algorithm for performing many walks. And let's try to see how this can be used to estimate PageRank. So first of all, what is PageRank? PageRank is a measure of ranking nodes on the graph. And intuitively, a PageRank measures the following. Suppose you start from any node. It doesn't matter where you start. Perform an extremely long walk. The probability of ending up at any given node is the PageRank of that node. So the probability of ending up at a node after a long walk is the PageRank value of that node. And this is used on the web and even social networks for ranking nodes. And it is computed frequently. So more formally, what is PageRank? One can define it in terms of the walk. So specifically, the random walk can be defined as a transition matrix where the ijth entry determines the probability of transitioning from I to j. And the distribution after L steps of the walk is just a to the L times the initial vector. And the PageRank distribution is the steady state distribution. That is, after performing an infinitely long walk. And clearly, you cannot perform a walk of length infinity. So typically, you perform it for a certain number of steps, after which the distribution is close to the steady state distribution. And this length is called the mixing time. So what you're interested in is the distribution after mixing time steps of the walk. And so you're trying to understand this PageRank value, PageRank vector. So how has this been done traditionally? So one of the standard implementations is some form of matrix vector multiplication. There are many different ways to think about it, but what is essentially going on is an iterative matrix vector multiplication. Again, recall that in this streaming model, you have linear space. So that is enough space to store a vector. But that is not enough space to store the matrix. And what you're getting in a stream is the entries of the matrix. And it's not too hard to see that in one pass, you can perform this matrix vector multiplication, one multiplication. And you're interested in m such multiplications. You want the distribution after m steps. So this can be done in m passes and linear space. So in our approach, we don't do any of this matrix vector multiplication. We have now a very good, efficient algorithm to do random walks. So try to use that. So a random walk of length m is exactly equivalent to sampling a node from this distribution. A random walk of length m is sampling one destination from this distribution at length m. So now, since we can do many walks, our goal is to perform many walks of length m. As you get you perform more and more walks, you get more and more samples from the distribution you want. And once you get sufficient number of samples, you can estimate the PageRank value of every node. And notice that we do not know m beforehand. So you are given a graph, and I want the PageRank distribution, but I do not know the mixing time. So how do I figure out what length walks to do? So in the paper, we actually show how to estimate the mixing time. And once you estimate the mixing time, you do these walks of length mixing time and get a PageRank estimate. So what does this give us? It gives us a way to estimate PageRank in root m passes and linear space. And using the alpha parameter I mentioned, if you can sort of trade off between the passes and space. In particular, for one choice of alpha, if you're willing to compromise on the passes from root m to m to the 5/8, you can bring down the space by a factor of m to the 1/4. And now compare this to the standard implementation that takes m passes and space. We significantly save on both, in passes as well as space. So this technique was, we use this technique for other settings and applications. So in particular, this streaming algorithm, we showed how to use this to perform graph partitioning efficiently in sublinear space, which is nice because there really has been not much work, or very little work, if any, on doing anything interesting in the streaming model in sublinear space. And then we also extended these techniques to do random walks efficiently on distributed networks. So the technical challenge turns out to be much harder in distributed networks because the setting is very different, but the high-level idea is really the same. And random walks have been performed for decades in this setting in many applications, because in distributed networks, one of the key applications is maintaining strong connectivity, and random walks are a good measure of the connectivity structure. So we first gave a deterministic algorithm to perform a walk of length L, and also extend it to many walks, in L to the 2/3 diameter to the 1/3 rounds. And typically, these peer-to-peer networks have small diameter. So in that case, this significantly improves on the naive L-round algorithm. And in more recent work, we further improved this to a square root length times diameter randomized algorithm. And also, we show an almost matching lower bound, assuming the diameter is not a factor, for performing single random walk. And this sort of tells us that we are stuck at root L for whatever reason. It's not clear how to improve further. And again, so these results can be used. We show how these results on distributed networks can be used to estimate mixing time and sample from random spanning trees. Specifically, this approach gives the fastest algorithm for estimating the mixing time of any given network. And also, we give the fastest algorithm known for sampling from random spanning trees. And random spanning trees, while theoretical property, it's really useful in distributed networks for routing. For instance, random spanning trees can be used to construct good expanders.
Can you say what would be, how fast do these algorithms run for mixing time and random?
Yeah, so I mean, so for mixing time, it really comes to something like root of mixing time rounds. So in root of mixing time rounds, we show how to estimate the mixing time of the graph. And no, so actually, yeah, that's why it doesn't make much sense for me to tell you how much time it takes, because this is a distributed network model, which I'm not going into at all. So it's really a very different model. It's this local model where any node can talk to its neighbors, and you're trying to do this global operation. So, I mean, we can talk offline probably about this, but it's a different model. And again, the naive technique is, so you measure rounds, and the naive technique is L rounds, and it has been used, and one can do better. So to summarize this, so this kind of brings me to the end of the first part of the talk. So we've broken past this linear time or sequential nature of random walks and shown how to apply this to streaming algorithms as well as distributed networks. And for distributed networks, we also show a lower bound, but are there better streaming algorithms, or is there a lower bound? This work also presents one of the first sublinear space algorithms for doing anything interesting in the streaming model, even though streaming algorithms have been around for quite a while. So are there other such algorithms out there? And from a practical standpoint, really you're dealing with these massive graphs that now you cannot even assume are stored on one disk. They're parallelized. They're stored on this distributed architecture such as Dryad or MapReduce. And so this is done both for efficiency reasons as well as the constraints because of the scale of the graph. And so it would really be interesting to extend some such techniques to these distributed architectures. Yeah, so that brings me to the end of the first part of the talk. Second part is much shorter. So before I shift gears, if you have any questions, I can take them now or at the end of the talk. Okay, so the second part is much shorter. I'll present some recent work on understanding ranking mechanisms on the web. So ranking is really ubiquitous. You see it in web search, in blog rankings, in forum rankings, social networks, question answering sites, online shopping where there are products, and movie ratings and so on. So on this list, the web search ranking is very different from the others and has been extensively researched. We are trying to understand rankings where the site is trying to use user feedback or user ratings to come up with a ranking on all the items. So here are a few screenshots where this happens. So on Dig, users post URLs, and you can go and dig something by saying that, which is equivalent to saying that you like that item. And again, in YouTube, users provide feedback by rating videos as stars between 1 star and 5 star. On Hot or Not, you can rate pictures between 1 and 10. And forums, you can give thumbs up or down, or again give star ratings. And similarly, in many such cases, Amazon product ratings, Facebook status messages, question answering sites, the match-in game, and so on. So there are several such situations where you're getting user feedback to come up with rankings. So what are the popular methods? The two most popular methods are star-based ratings, as well as thumbs-based, where you can give thumbs up or down, or sometimes you can only give thumbs up. But there are more elaborate mechanisms, such as where users acquire reputation. So votes from specific users are more important, and comparisons and votes. So in any of these sites, what is the general architecture by which users interact with the sites? So there are two fundamental ways. One is clearly users posting new items. So users go and submit new items, and the new items get stored in the database. But there's also this aspect of the ranking, so users providing feedback on items. So whenever a user provides feedback on a certain item, you sort of update the score of that item, and you want to learn the relative scores of all items, and then you feed back the updated score to the database. And the question is, how do you pick items? So how do you leverage the user feedback to the best to get a good ranking? So what is under your control is this review module. So key question is, how do you pick items to get review from? So let's try to understand this in a little more detail. So what really goes into a ranking mechanism? What are the decisions you need to make? So one question is, how do you seek reviews? So it can be floating. By floating, I mean dissociated from the display, where on the given site, you allow users to provide feedback on one part of the site, but users are allowed to browse on the rest of the site. Or it could be tied, or along with the display, where users are allowed to browse anything they like, and as they browse, they can vote on anything they like. So you need to make this decision choice. Another choice is what sort of feedback do you allow? Star-based or comparison-based or thumbs-based? In case of stars, how many stars do you allow? 5 or 8 or 2 or so on. And another key question is, in what order do you display the items? So even if the feedback is in terms of tied, in terms of the tied system, where users are free to browse on anything they like and vote on anything they like, I can bias the user to provide feedback on what I want by changing the order in which I display the items. So for instance, I could try to display the new items such that I get quick feedback on them. But then users are not seeing the best items. Alternatively, I can show the best items on the front page, but then users are more likely to vote on that. And then you do not get you suffer from this rich gets richer problem. So you might want to do some kind of a trade-off between them. And then there's this question of, how do you update scores? When I get feedback from users, how do I update the scores of the items that have been reviewed such that I come up with a ranking? And a final very crucial aspect is, on any of these sites, the users submit. So the activity in terms of submitting new items is extremely large. It's at a staggering rate at which users submit new items, but not nearly enough feedback. Very few users take the effort or the time to really go and provide feedback. So is there a way to incentivize this such that I get better feedback, or provide a reason for users to give me more feedback such that I learn the ranking better? So, okay, so we'll come back to that in a bit. So given the ranking mechanism, how do I evaluate whether it is good or bad? So clearly, I want good rankings. Based on the feedback I get, I want quality of ranking to be high among all the items in the database. But I want the ranking, I want to achieve a good ranking quickly or with minimal review bandwidth, because of what I just said, that you get much less feedback than you would like. So one specific question is, with bounded feedback per item, with constant feedback per item, can I get fairly accurate rankings over all items? So is this even possible? So we'll come to that. And a third aspect to understanding whether a mechanism is good is latency. By this I mean whether you're keeping the users satisfied in terms of giving them quick feedback. So suppose I go and post an item and I want feedback on this. Really, I don't want feedback to arrive 10 days later. I don't want a thumbs up 10 days later and 2 thumbs up 30 days later. I want to keep so a site wants to keep the user satisfied. You want to give quick feedback such that they remain happy. So how do you do this? That's what I mean by latency. So our results in this work is informally stated the following. In terms of theory, what we show is that under certain assumptions on the inherent score distribution of all items and voting patterns, we show that we provide a comparison-based ranking mechanism by which you can achieve accurate rankings with just bounded feedback, with constant feedback per item. And what is worse is we show that for the standard techniques of thumbs and star-based rankings, you cannot achieve constant. There are parameters for which you cannot achieve accurate rankings with similar amount of feedback. And then we have a system that implements this comparison-based ranking mechanism. And we perform experiments both on our system as well as synthetic data. And the experiments actually corroborate the theorem, suggesting that, yeah.
So what you so the previous slide,
yeah.
You said there's a notion of the quality of rankings.
Right.
What exactly is
so, I'm being a little vague here. So what I, so I'll mention this very briefly at the end again. So, but roughly what I mean is that you have these items. All items have some inherent score or inherent quality, I'm assuming this, which I do not know. So given an inherent score of all items, there's a ranking of the quality of all items. So the best one is the one with the inherent highest score, and the second, and so on. And there's this inherent ranking that I'm trying to learn.
So is the inherent ranking based only on the feedback?
No. So this is a ground truth. This is a fundamental truth, the inherent ranking, or inherent scores that I do not know. It's just that there is something that is better for everyone. I'm assuming this. There is some item that is best, which I do not know. There's something that is second best. This is just a law, let's say. And I'm trying to learn this ranking. So, yeah. So,
And this learning is based on what?
So the learning is purely based on feedback from users. And the question is, how do you get this feedback? So I'll mention a little more, and we can talk more offline about this. Yeah, so our experiments also suggest that a comparison-based mechanism is superior to thumbs or star-based. So let's try to understand the intuition for this. So what is happening in a star-based mechanism? So usually you have this pattern where the site operates in a way where users are allowed to browse anything they like and vote on anything they like. So then they suffer from this rich gets richer problem that I mentioned. But what is really one bad aspect about this is there's some sort of unnormalized ranking going on. Users are voting on items independent of the quality of other items. So there's no normalization. So one user might be highly generous in giving star ratings. Another user might be extremely restricted in giving good ratings. So how do you really reconcile this situation? And the incentive is a question often. So in case of comparisons, what we do is we explicitly seek feedback. We present users two items and ask them to compare. Tell us which they prefer. And so this results in automatic normalization. User is not voting on an item independent of the quality of the other ones. So user is saying this is better than that. So if the first item is really better than the second item, then every user is more likely to vote on the first than the second. So a disadvantage could be that users are not free to vote on what they like. Users we only seek feedback explicitly. And another question is it too expensive? So another comment on that at the end of the slide. So where can we use some such comparison-based mechanism? So clearly any mechanism can be used anywhere, such as public forums, ranking of blogs, online shopping sites, and so on. But let's try to understand YouTube. A comparison-based mechanism might not be the best choice there, because if I present a user two videos and ask him which one he prefers, and he has to look at both 4-minute videos and then decide I prefer the first. The practicality is really questionable. Why am I asking the user to invest so much of his time? And then peer reviewing of papers. Currently we operate on this star-based mechanism where reviewers give scores to independent papers, and there's no normalization. And you're reviewing papers for different conferences and different users. Yeah.
You can go back to your slide that has the results.
Yeah.
You mentioned that in the star system, it's impossible to learn that.
Right.
But it might be possible if you also model the user. Like you can also eliminate this normalization that one user gives higher ratings when compared to another user on average. If I also know which user marked these things, won't I be able to work out?
Maybe it may be, but right now we're working under the setting where you have anonymous users. So I'm not trying to learn anything about the user. And secondly, here I'm looking at, I'm saying that it's not possible with bounded feedback. With more feedback, even under this setting, it may be possible. So unfortunately, I'm not really going into the theorem in too much detail. But in this setting, we're really looking at anonymous users. And there is a model under which users vote. That also I'm not presenting, but we can talk offline about that. Yeah, so these are the various areas. So let me try to quickly describe our system where we implement the comparison-based mechanism. So it's called ShoutVelocity, and It's available at ShoutVelocity.com. So it's something like a Twitter dig site where users can post short snippets. It could be a joke or a saying or a quotation or a link to some other site. And the comparison-based mechanism explicitly seeks feedback. So we present users two items to compare, and then they have to say, I prefer first over second. A bit more on that in a minute. And for how do we pick items? That's a fairly elaborate mechanism, but one aspect to it is we try to pick items with higher ranks or better quality with higher probability, such that you get more accuracy at the top. And this also mimics the current systems where the best items are displayed on the top. So again, that's only so much about that. So here's a screenshot of our system, ShoutVelocity, where you see shouts by different users and the scores on the left. And so here we've ranked all the shouts in decreasing order of scores. So the top one is the best one, second is the second best, and so on. And one can order this based on recency also. And whenever a user, so in our site we call the items as shouts. So whenever a user submits a new shout, she is redirected to a page like this, where she is displayed two previous shouts. Here one by Akhil and one by Sin. So she has to say, I prefer Akhil's shout over Sin's, or the other way around. And in addition, you can attach smileys or comments with both of them. So this is the mechanism by which we seek feedback. So is there an incentive for the user to provide feedback? Why should the user be randomly redirected to a page where she has to vote between two previous ones? The reason is only if the user submitted something where she wants feedback right now, only then she is required to vote the previous items. If not, she can she can browse and post unhindered. So only if a user wants feedback on what she posted, she has to invest the time to review previous items. So that results in an incentive for the user to vote. And do we have sufficient bandwidth? Yes, because for every one new item that needs a vote, we have two previous items that get voted. So there seems to be a sufficient bandwidth in terms of votes. So again, to recap the theory results, again, this is really not stating them in full precisely, but roughly we assume that the inherent scores of all items are normally distributed, like a Gaussian, and there's a probabilistic voting mechanism, as well as a probabilistic thumbs-based mechanism. And under such a mechanism, we show that we can get fairly accurate rankings with bounded feedback, but a thumbs-based mechanism or a star-based cannot. And we perform experiments on synthetic data as well as real data. I'll just present two graphs to give you a flavor. So for the synthetic data, we generate 1,000 players or 1,000 items with inherent scores, sampled according to the Gaussian. So these are the ground truths. And now you're trying to learn the ranking on them. So the algorithm does not know the ground truth, but the probabilistic voting mechanism is determined by the ground truth. So a higher one is likely to be voted with greater probability. And in our system also we perform experiments. So far we have something like 1,200 items submitted and close to 5,000 comparisons. So here's a plot that shows on the x-axis the number of comparisons, and the y-axis the mean reciprocal rank, which measures the accuracy of the top position. Specifically, if mean reciprocal rank is 0.5, then you are getting the best item at the top half the time. And on the x-axis, the number of comparisons is for our comparison-based metric. In case of thumbs, we allow twice as many. So if I'm comparing x comparisons, that is compared to 2x thumbs votes, just to be fair. And the dotted lines here represent the accuracy of a thumbs-based algorithm, so for different parameters. Again, I'm not going into the specifics of the parameters. And the solid lines represent the algorithm for comparison-based, again, for different parameters. Yeah?
So in the comparison thing, you can get cycles, right? So how do you deal with that?
By cycles, you mean A beats B, B beats C, and C beats A? Yeah, you can get that. So the thing is that you have a set of items. We choose how items get compared. Given a set of comparisons, how do we learn the ranking? So and now it's not something like that A beats B implies that A is higher than B. So there is a mechanism of there is a way to, so we have an algorithm to go from a set of comparisons to a ranking. And it is not determined just by who beats whom, but I mean, who do you lose to, their scores, relative scores, how many times have you been compared, and several such criteria.
But there is no algorithm that we suffer from paradoxes.
By paradox, you mean the cycle?
Yeah, if I have one.
Yeah. So the point is, suppose A is better than B, B is better than C, then sure, C might still win over A. But if I compare C sufficient number of times, okay, there might be one anomaly, but overall, averaged out, you'll see some kind of nice behavior.
Well, you can't guarantee that in general. Because R is paradox. It tells you that any system you choose to combine individual rankings into a global order, will suffer some kind of inconsistencies or paradoxes.
Yeah, sure. So the goal is the larger the number of comparisons you do, the fewer the inconsistencies will be. So as I do more and more comparisons, I'm getting better and better accuracy. So we can discuss more about that. Okay, so this is one, and now the latency that I briefly mentioned, you want to keep users happy by providing them feedback very quickly. And on our system, so the x-axis plots the latency and the y-axis the fraction of shouts. And I measured latency as a number of new items that get posted before your item gets voted. And on our system, most shouts have a latency between 2 and 6. So it's sufficiently small. And we're keeping users happy in terms of, so this is on our system, what is happening. Okay, so that concludes the second part of my talk. So we presented comparison-based ranking, and there are several extensions to this possible, such as comparing only based on categories. Because how do I compare a joke with a philosophical statement? It's not clear how to say one is better than the other. And we presented the ShoutVelocity system, analyzed previous mechanisms such as star ratings and our comparison-based mechanism. One could think of generalizing the pairwise comparisons to n-wise comparisons, but practicality is fairly questionable, I think. And should we be using this for paper reviewing or for any of the current situations? Okay, so that finishes the second part, and I'll take 2-3 minutes more to just mention all of my work. So broadly speaking, I've worked on algorithms, and my algorithmic problems are motivated by the World Wide Web, social networks, databases, and distributed networks. So the first part on estimating PageRank I mentioned appeared in Pods. The subsequent work on graph partitioning or finding graph cuts appeared in ESA a few years back. The results that I mentioned but did not talk about on performing random walks in a distributed network, the first part of it appeared in Pod C last year. And the subsequent improved work is currently under submission. A while back, I worked on query search result diversification, and this appeared in KDD 2 years back. The second part of the talk, where we have this system, the system has been around for 2 years now, but we wrote a paper very recently, which appeared in Wisdom a few weeks back. And in Wisdom, I had another paper on understanding graph distances between nodes. So graph distances has been extensively studied in literature. But when you're dealing with these massive graphs and you want very quick online distance computation, this raises several issues. So there are theoretical techniques, but let's think of a case where you have hundreds of millions of nodes, and at query time, I get 2 nodes. And I want the approximate distance between them in milliseconds. How do you do this? So we have some work on this in Wisdom also a few weeks back. And a while back, I worked on computing skylines. So I won't define this, but skylines is a measure of representing a database. So given a large database, how do you represent it by a small set of tuples that is interesting from the perspective of users? For instance, hotel websites. A user goes and searches for hotels. There are thousands of hotels, but you want to present 10 of them, such that you maximize the happiness of a given user. So how do you, so skylines is one way to capture the interesting hotels. And we present the fastest known algorithm to compute skylines, which is an exponential improvement over the previous best known. And skylines have been studied for over a decade, about a decade in database literature. And some similar work on representing databases is under submission. Very recently, I worked on making social recommendations in a privacy-preserving manner in social networks. So this is currently under submission. And I have a set of other small results on understanding different streaming models, markets, routing networks, finding dense subgraphs, understanding information spread on social networks, and so on. Yeah, thank you.